Humans can and do have an impact on the Earth's atmosphere. Most notably, humans put all sorts of pollutants into the atmosphere. These pollutants include agricultural dust, industrial chemicals, byproducts of fossil fuel combustion, etc. Some pollutants, such as particulates, impair visibility. Some pollutants are hazardous to human health, like particulates or carbon monoxide. Some pollutants react with other pollutants to form other forms of pollution, like smog. Some pollutants impact natural ecosystems, such as sulfur dioxide, forming acidic rain. And some pollutants, like CO2, impact our global climate. Notably, many pollutants have multiple effects. In a future lesson, we will look more closely at carbon dioxide and methane and nitrous oxide and other greenhouse gases that are pollutants that contribute to climate change or global warming. In this lesson, however, we're going to focus on one impact of anthropogenic or human-generated pollution, the destruction of the ozone layer by pollutants that are called ozone-depleting substances. First, and notably, there's really no layer of ozone. Rather, there's a region in the upper stratosphere that has a higher concentration of ozone than elsewhere in the atmosphere. Thus, instead of referring to a hole in the ozone layer, it's more precise to simply talk about stratospheric ozone depletion. Some of the ozone in the stratosphere is simply being depleted. It's being destroyed. As I mentioned earlier, this is pretty much the only time in the course that we're going to be talking about the stratosphere. Most of what we talk about in this class is the troposphere, with the exception of stratospheric ozone depletion. So what is ozone and why is it important? Well, chemically, ozone is 3 oxygen atoms bonded together. The oxygen that we breathe, on the other hand, is diatomic oxygen. It has 2 oxygen atoms bonded together. Very different substances. As we mentioned, diatomic oxygen is the second most abundant gas in the homosphere, the troposphere, stratosphere, and mesosphere, where it comprises about 21% of the atmosphere by volume. Ozone, on the other hand, is a trace gas. Now, we're going to be interested in talking about stratospheric ozone, but check this out. Ozone does exist in trace amounts in the troposphere. In fact, ozone is a very important anthropogenic pollutant in the troposphere. It's created when nitrogen oxides, perhaps from your car, combine with volatile organic compounds in the presence of sunlight. It's a photochemical reaction. These precursor compounds, nitrogen oxides and volatile organic compounds, are emitted from car exhausts, industrial facilities, etc. And notably, when we have spare the air days here in the San Francisco Bay Area, it is often due to elevated tropospheric ozone levels. Ozone is a major component of smog, and it can damage our lungs. For more excellent information on tropospheric ozone, or ground-level ozone, see the United States Environmental Protection Agency website shown here. Alrighty, so tropospheric ozone is an anthropogenic, that means human-created pollutant, and it's bad for us down here in the troposphere. So bad nearby. On the other hand, up in the stratosphere, this is where the good ozone exists. So again, to review, in the troposphere, ozone is a pollutant that damages our lungs. But in the stratosphere, ozone is beneficial. It's naturally formed, and it blocks UV radiation. Ozone is naturally created high in the stratosphere when ultraviolet light breaks down a diatomic oxygen molecule into two oxygen atoms. These lone oxygen atoms combine with another diatomic oxygen molecule to form ozone. Thus, in the process of forming ozone, some ultraviolet radiation is absorbed, and thus it does not reach the Earth. So this is how ozone forms naturally in the stratosphere. Ozone is also naturally destroyed in the stratosphere. When ultraviolet radiation breaks down an ozone molecule back into diatomic oxygen and an oxygen atom, you'll see that during this process, more ultraviolet light is absorbed and thus blocked from reaching the Earth. Yay! So through this natural process of ozone being created and destroyed, ultraviolet light is absorbed by ozone and blocked from reaching the Earth. This natural process of ozone formation and destruction happens in the upper stratosphere and blocks harmful UV radiation from hitting the Earth and from hitting us. For millions of years, this process has been in equilibrium, and it's worked in the same manner. Organisms on Earth, in fact, have evolved to be best adapted to the amount of UV radiation that naturally gets to the Earth. So a system in balance, until humans invented new anthropogenic compounds that damage stratospheric ozone. There's a whole group of chemical compounds, generally all anthropogenic, that we call ozone-depleting substances. These substances were created for a variety of uses, but what they all have in common is that they destroy stratospheric ozone and thus allow more UV radiation to penetrate the atmosphere and reach us here on Earth. The most potent and also well-known compounds in this group are called CFCs, chlorofluorocarbons. They contain chlorine, fluorine, and carbon. However, they're not the only compounds responsible, and they have pretty much now been banned from use. Notably, in California, methyl bromide, which is used to kill fungi in the soil and thus protect low-growing agricultural crops like strawberries and tomatoes from pests, is also an ozone-depleting substance. This was supposed to be phased out by 2016, but California still has an exemption from this international treaty for conventionally grown strawberries. Let's look a little deeper into CFCs. They're completely anthropogenic, made by humans, and they are formed of chlorine, fluorine, and carbon. When CFCs were first created, scientists believed they were inert, which means non-reactive, and posed no threat to human health or the environment. Indeed, that seemed to be the case, at least in the troposphere. CFCs were widely used as refrigerants, solvents, propellants in aerosols, and to make styrofoam. Eventually, though, the molecules released into the troposphere made their way up into the stratosphere, where there is an abundance of ultraviolet radiation, UVA, UVB, and UVC. And these compounds that were stable in the troposphere were easily broken down in the presence of intense solar radiation up in the stratosphere. Whoops. Not so inert up in the stratosphere. Study the diagram here to see how CFCs and other ozone-depleting compounds destroy stratospheric ozone. Consider stopping the video to check this diagram out. You can see CFCs break down under UV light and lose chlorine atoms. These chlorine atoms can rip an oxygen off an ozone molecule and form chlorine monoxide, and also, in the process, an diatomic oxygen molecule. Then the chlorine monoxide combines with an oxygen atom to form another molecule of diatomic oxygen and a free chlorine atom. So through this process, an ozone molecule was destroyed. And notably, notice that this chlorine atom is now free again and free to go take out another ozone molecule. In fact, one chlorine atom can likely destroy 100,000 ozone molecules before it eventually drifts up into the mesosphere. And that's just one atom of chlorine. A chemical substance would have thousands or millions of atoms of chlorine. We've done great work in reducing the number of ozone-depleting substances that are released into the atmosphere. In particular, many CFCs have been banned and are no longer created or used. However, we're still dealing with CFCs that have been released previously. They're still up in the atmosphere, going through this cycle and depleting ozone. So where is ozone depletion most severe? Well, ozone depletion is a global problem, as ozone has thinned everywhere. However, ozone depletion is the most intense and severe over the Antarctic during the southern hemisphere springtime. During the southern hemisphere winter, a circumpolar vortex is formed around the South Pole region. Basically, this is a region of very cold air that does not mix with the air further to the north. This same phenomena exists in the northern polar regions as well, but there's more land there to break up wind patterns and allow more mixing. So this cold air in this vortex is isolated, and the clouds within this region are formed mainly of ice crystals, as it's very cold, not liquid water. Ice crystals are very effective at attracting and accumulating chlorine-based molecules. When spring arrives and the ice crystals melt, then all of a sudden an enormous amount of this chlorine is released all at once and starts to destroy the ozone all at once. Thus we get an ozone hole phenomena, a region of extreme ozone depletion, over the Antarctic each spring as that cloud ice is melting. Over the year, this low ozone air mixes globally, thus thinning ozone everywhere. As noted, the same phenomena exists over the northern pole, but it's just not as severe because there isn't as an extreme circumpolar vortex in the northern hemisphere. So why do we care about this, and what can we do? Well, as stratospheric ozone is depleted, that means more harmful UV radiation penetrates the atmosphere and reaches the Earth. This extra UV radiation causes sunburns, skin cancers, cataracts, crop damage, and damage to natural ecosystems. For example, the photosynthetic bacteria, or to fish, amphibians, and trees, etc. Globally, great work has been done to decrease stratospheric ozone depletion. In fact, it's likely one of the most effective global environmental efforts ever. A global treaty was signed called the Montreal Protocol. It was signed in 1987 and has been amended many times since. And it's actually been signed on by every nation on Earth. The treaty banned the production of CFCs and the use of selected other compounds, other ozone-depleting substances, and it continually is updated as we learn more about what sorts of substances are ozone depleters. The treaty also worked hard to find alternatives to the existing ozone-depleting substances, and it required the developed countries to act first and also to share knowledge with the less developed